This is logic coding. Today we're actually going to look at our first hard problem called robot room cleaner. And from now on, I will make videos in the format of the interview, which will contain the 4 elements. So the first, we want to understand the question, ask clarifying question if necessary, and analyze the edge cases. Then we want to explain our algorithms and maybe write down the pseudocode step by step and analyze its running time, maybe spatial complexity as well. Then it comes to the coding part. I want to evaluate my code through correctness, readability, as well as its speed. And the last one, I also come up with a simple testing case for my algorithms to test my solution. So this problem is it's like Zomba. It's like a robot cleaner in a room modeled as a grid. So we would have a grid. Each cell in the grid can either be empty or blocked. The robot cleaner are given 4 APIs, which are first, move forward, and then turn left and turn right. Each turn it makes 90 degrees. When it tries to move into a block cell, its bumper sensor detects the obstacle and stays on the current cell. So our goal is to design an algorithm to clean the entire room using the only 4 APIs shown below. So this interface already provided as those 4 functions, where the first one is kind of like an obstacle detection. This is very important because when we traverse a grid, it is important to detect obstacles and boundaries. So this move function can tell us about the information. And then the robot can always stay at the current cell and turn left and turn right. And it also has the clean operation. So let's look at one example. So in this example, we have the grid given and we have the initial position of the robot. And our goal is to clean every ones in the room. So 0 means it's blocked, all the ones means the cell is accessible. The robot initially starts at position this, from the top this. So now it might be important to ask some clarifying questions. It is interesting to know where this robot is and why our input, there's no grid information. So the input is given only to initialize the room and the robot position internally. We need to solve this problem blindfoldly, and we can only control the robot using the aforementioned APIs without knowing the grid and the initial robot position. The initial position will always be in an accessible cell. The initial direction will be facing up. So for the states, right now we know that the states will include ij and facing directions for the robot. And all accessible cells are connected, which means the cell marked as 1 will be accessible by the robot so it can finish the job. So the edge cases is it can start and finish the clean job. Assuming all 4 edges of the grid are all surrounded by a wall, so we don't need to do boundary condition. Cool. After this stage, we understand the question, we understand our input, our robot's interfaces, and we understand our goal is to clean the whole room. Now let's think about possible solutions. So we know that at each cell state, we want to clean the room and go to the next room, accessible room. So it is natural to think using recursion plus backtrack. At each cell, we can do the clean function recursively. However, at each state can explore in 4 directions. We can explore in 4 directions, and the constraint would be whether we have visited this cell or the robot can move within the cell. If it can, then we recursively call our DFS or our backtracking algorithm, and then restore its original state. If not, we prune. So the time complexity of this algorithm will be O(n), where n is the number of ones since it's all accessible cell. And by introducing a unordered set to keep track of the positions that this robot has already been at, it can avoid duplicate clean or duplicate visit. Within that, I think we can start to write our code. Before, let's define our 4 possible explorations. Directions. Initially, it's facing up, so up is 0. No, it's -1, 0. And then facing right, it's 0, 1. And then down, it's 1, 0, and it's 0, -1. So we have 4 directions to explore. And let's define an unordered set with string to represent the state. Let's say it's visited. State is ij. And then we recursively call the DFS where we have this robot, we have the states, and we have the cell number. Let's assume it's starting from 0, 0, since all the directions are relative, and we have the original facing directions as well. Now let's dive into this DFS function. So the first input is this robot, and then we pass this visited as a reference since we need to modify it. And then we have the cell as well as the facing direction. The first thing we need to do is clean the current cell and mark it. So we need to do robot clean at this current cell, and we need to add this one to our in. So the state can be expressed as toString. We do this, and we do toString j. We do visited insert. And the next is to explore 4 directional. So we would have 4 choices. K++. For each direction, we would have a next facing direction will equals to k plus whatever we are facing right now, module by 4. Then with the given next facing direction, I can have my next position as directions and facing directions 0. The same way I can get my next I, next j, which is the first component. Now I want to check whether we should go explore in next. So if it satisfies the constraint where the constraint is it's not in visited, so let's do string next state equal to this one, change this to next I, I'll change this to next j. If it's not visited and the robot can actually move to that facing direction, then we DFS. We DFS next I, next j, and next facing direction. After this DFS, though, it is important to restore to its original direction. How can we restore its original direction? So, for example, if I'm here at and I'm facing to the right and I move to here, if I want to go back from this position to this position, what I need to do is first turn 180 degrees, turn 2 times right, move to this position, and then turn 180 degrees again. So I need to do robot turn right 4 times, actually. Within between, I need to move the robot. Cool. After each direction, in order to change from one facing direction to another, is not only I need to change k, I also need to change the robot facing direction manually by making this robot turn right. Cool. Now let's check about the code. So the algorithm is a recursion plus a unordered set visited. We have the state, and then we explore 4 directionally. We get the next phase if it's valid. If it's valid, we explore. After explore, we backtrack. Cool. Let's try and run this. I should do count. Nice. Let's try and submit. Great. That's it.